Hello, chemists. Jolly here again. Let's continue our discussion on proton NMR. So I'm back to the notes, and I'm not doing them in specific order. I'm kind of leading up to the overall picture. So we're going to talk about the integration of peaks next. All right, so we already talked about equivalent versus non-equivalent. Okay, that's how many peaks are totally in there, but I want to know how many hydrogens are actually part of each of those. So that's called the integration of peaks. So basically the magnitude of signal indicates the number of protons present. Okay, height is relative. It is dependent on the integration of the curve that the computer does. And so we can get fractions. So a 1.5 to 1 ratio, well, you can't have 1.5 hydrogens. So that would indicate a 3 to 2 ratio, okay? Or you could go all the way up 6 to 4, or you could keep going. So just remember, when we do integrations, it's a ratio. Generally, the smallest ratio is the one we're looking at, but that's not always true. What you're going to see is something like this. Okay, there will be a peak, and let's not do red. Come on. All right, so we'll say we have a really tall peak, and we'll have, you don't know about the splitting yet, but that is a peak. It's called a triplet. And then the computer will integrate this. And luckily for you, you don't have to determine the area underneath it. We used to have to do that. But so from here to here, the computer will ratio that, and then it will also integrate that from there to there. And then it will compare the two sizes. And this one, okay, my drawing isn't awesome, but this looks like a 1 to 2 relationship, okay? Or going from left to right, that looks like a 2 to 1 relationship. So that could be a CH2 to a CH, or, oh, CH4. Okay, now if you have a CH4, it's not connected to anything, but this could also be 4 to 2, which would imply there has to be some kind of symmetry, or we could keep going and we could keep going. So this is one way that you will actually see the integration done. On a lot of the current proton NMRs, it will literally just tell you how many protons, and then you would see something like this. You would see a 1 above it, and you would see, oh, let me see, make it the same. You would see a 2 above it, and then you would see a 1 above it. And again, that is the ratio. Yes, it could be 2 hydrogens to 1 hydrogen, but never be afraid to, go up to the next ratio. Well, how are we going to tell how many there are? That's the nice thing. This is probably the simplest concept for NMR. Draw your hydrogens again. And we know there is going to be 1, 2, 3, 4 peaks. Okay, there's going to be 4 peaks. Well, when I'm looking at each peak, I just need to know how many hydrogens made that peak. So right now, I am only looking at those. And the question is, how many hydrogens, okay, imagine your thumb or under that box, how many hydrogens are making that peak? This one happens to be 3. So it should integrate for 3. Change colors. Let's try that color. This one, if you picture what's under there, that's 2 hydrogens. Ooh, let's do pink. This one is also 2 hydrogens. And then don't forget that hetero hydrogen on the oxygen, and we'll do that one green. And that's 1 hydrogen. And so each of those peaks will have the height, which is relative. And let's see, what is our relative heights here? We have a 3 to 2 to 2 to 1. So again, drawing is not my best feature here. But we could go something like, if that was the really tall one, and then 2, 2, and 1. Okay, so in the proton NMR, those peaks would have something roughly looking like that, or above it, it would tell you the relationship. Now I'm going to go back to that picture that we started earlier. And where are you? Okay. We're going to go back and we are going to determine how many hydrogens are going to be each of those, or integrated for each of those. All right. So again, let's do this wonderful alkane. And underneath that box, there's 3. Here, there's 2. Here, there's 2. And here, there's 3. Now, this is a very interesting thing because we said that those were not identical. Well, if they're not identical, they're going to show up in the same place, which means the peak is just going to be taller than we expect. So peak A is going to integrate for 6 hydrogens, and peak B is going to integrate for 4 hydrogens. Because remember, the peak height tells you how many hydrogens, and because they're equivalent, they show up in the same spot, so it is taller than expected. But that is not the smallest ratio, so we would probably see a 3:2 relationship on the spectra. All right, different color. How about this one? Let's look at this alcohol again. This one would be 3 hydrogens. This one would be 2 hydrogens. This one would be 2 hydrogens. And this one would be 1 hydrogen. So those peaks would be that height. This hetero, don't forget, anything that can hydrogen bond will tend to be a little bit more spread out. So most of the peaks are going to be sharp, except for those that can hydrogen bond. All right, so over here, 3 hydrogens, 2 hydrogens, 2 hydrogens. Don't forget that aldehyde has a hydrogen. So a 3:2 to 2 to 1 relationship again, a 3:2 to 2 to 1. Wow, I'm very boring. Okay, now down here, though, what color haven't we used? We'll go pink. This one, so C will integrate for 1 hydrogen. This one will integrate for 1 hydrogen, 1 hydrogen, 2 hydrogens, and 3 hydrogens. So if you'll notice, there's nothing different when we're talking about the integration. It literally is how many hydrogens are making that peak. All right, this one, A, will only integrate for 1 hydrogen, where remember this one and this one are the same. So just like the above alkane, those are the same. So that one will integrate for 2 hydrogens. The C's are the same, so that will integrate for 2 hydrogens, and 2 hydrogens, and 3 hydrogens. And then last but not least, let's do this alkyne. This one will integrate for 3 hydrogens, for 2 hydrogens, and 1 hydrogen. So we have now 2 different pieces. We can determine how many peaks should appear in the spectra, how many unique hydrogens, and then we also know how tall those peaks should be. And I'm just going to go now to the handout just to show you that example. And where are you? Handout. Show all windows. Come on. Come on. It's not moving for me. All right, let's stop that share and let's try again. Wow, my fingers are not being very sensitive right here. Sorry about that. All right, here is what I was talking about. So the green here is the height between this point and that point, the height between this point and that point, and the height between this one and that one. And so the computer for us is integrating that as a relationship of a 2 to 4 to 6 relationship, but that's not the smallest ratio. It will actually print for us a 1 to 2 to 3. And so that's what the integration would look like. And it won't always draw these integration lines for you. What we used to do is actually literally take a ruler and we'd measure those, and then we would divide them by the smallest. All right, that is it for integration. It's probably the simplest of the concepts for Proton NMR. And until next time, jolly out.